A new NVIDIA library, cuDNN. cuDNN, right?
cuDNN.
cuDNN. All right. So without further ado, since it's already getting late, I'll hand over the stage to Sharan.
Thanks, Rick. Hi, my name is Sharan. I'm a software engineer at NVIDIA, and I'm one of the developers who worked on this cuDNN library. Let's get started. For people who've been in this area, this is a slide that you've probably seen somewhere before. It's sort of the spectrum of the whole, the way machine learning is laid out today. And it's sort of, the two sort of orthogonal axes are supervised, unsupervised, deep and shallow. The application we're going to be working with today is a convolutional neural net. And that's sort of where it lies in this entire landscape of various machine learning algorithms. And the applications for this primarily are in the image and the audio field. In image, there are three big problems: classification, localization, and segmentation. Variants of this in different formats. Classification simply says, here's an image, tell me what's in it, or what's the subject of the image. Localization says, tell me what's in it and put a box around it. So that's what you see there, where you have child, dog, it says person. Segmentation is the hardest of these problems. It says not only do you have to identify the object, you need to be like pixel accurate. You need a pixel accurate depiction of what those are. So that's the picture on the right, where you have a soccer ball and two kids playing and a couple of others in the background, with each object identified to the accuracy of a pixel. Very briefly you can think of any artificial intelligence task as the evaluation of a really complicated function. So for instance, a facial recognition problem is a function that maps a bunch of pixels in the form of an image to a name or some unique identifier of the person. Immediately this is a problem, because as human beings, you and I are not designed to think of functions that look like this. That's just way too complicated. That's not what any of us learned in any calculus class or any optimization class that we ever took. And that's where neural networks come in. It turns out you start off with these relatively simple units called neurons. And if you connect enough of them together in a big enough network, you'll end up evaluating a complex function such as what you require for a facial recognition or a handwriting recognition task. A neuron typically consists of two phases. The first is usually some kind of linear transformation of the input data. Doesn't have to be, but this is what you see usually. A linear transformation of the input data, and then you take the output of this linear transformation, and to each of those points, you apply some kind of a nonlinear function, like a step function or a sigmoid function, something very simple. And so the neuron is quite simple, and it evaluates some nonlinear function of the input data. And as I said, the network consists of connecting a bunch of these up together in some kind of an arrangement. A CNN, a convolutional neural network, is one in which this linear transformation phase is a convolution function. These are two of the seminal works in this field. The first one represents a network by Yann LeCun for handwriting recognition that's used quite often when you scan, for instance, check into your ATM machine, or if you, in the postal services, to decode addresses that are written by hand. The second one is by Alex Krzyzewski and a bunch of other researchers. It's used in image recognition tasks, and in 2012, this won the ImageNet, ImageNet recognition challenge by a huge margin. And since then, that's what sort of drove the second wave of interest in convolutional neural networks, especially for image data. This is what it looks. This is sort of the spread of teams that have been using GPUs for their training and convolutional neural networks in the recent past. 2012, as you see, was where Alex Krzyzewski first came out with convolutional neural nets for this image recognition challenge, and he produced a very significant drop in the error rate, almost a 10% drop. And since then, the last 2 years, there's been a lot more teams using GPUs, and the error rate went down this year to 6.5%, which is the classification error rate, which is pretty impressive. And all but 2 teams, to our knowledge, use GPUs. One team definitely did not use GPUs, and the other team were not sure. So if anybody does know, we're happy to find out. cuDNN, the name is sort of meant to be similar to cuBLAS or cuSparse, and in that same sense, it provides a bunch of low-level primitives that are used to accelerate like the numerical core of these DNN applications. It's not a full neural network library in itself. It just accelerates the computational chunk. That's the work that GPUs do. The idea is to be easily usable and easily integrated into all kinds of deep neural network frameworks. We develop and maintain it, and it is optimized for the current generation and will remain optimized for the future. That's the big advantage of this library, which is that the people who develop the frameworks for neural networks don't have to sit there optimizing their kernel for every new generation of hardware that comes up. That's taken care of under the hood in this library. The first release has been focused on convolutional neural networks. Those are what the routines that we have right now. In the future, we're looking to expand beyond that to other application domains and other kinds of neural networks. We'll be happy to hear from you guys about what you think we should be doing in the future. CNNs work in this sort of work. You can think of them as like in a computational sense as a stack of repeated triplets. You have a convolution function, which is the main sort of the heavy lifting. All the floating point work is there. It represents close to 80 to 90% of the entire time that it takes to train an entire neural network. Followed by a max pooling and then some kind of a pointwise activation function. Overfeed is one example of a convolutional neural network that's been used successfully for classification problems. That's what it looks like. A little bit more about what these parameters mean will come later. As I said, the convolution problem represents the linear transformation part of the neurons that are used in convolutional neural networks. This, what I'm going to be talking about in the next couple of minutes, is sort of the broad mathematical work that needs to be done in these linear transformations. I'm going to call it the multi-convolve, but for anybody who's familiar with a 2D convolution, you'll see very quickly that it's really, really similar to what you've seen before, with just some amount of generalization added on. So it's like a 2D convolution. You start off with an image and a filter. You superimpose the filter on top of the image, do a pointwise multiply and sum, and that gives you one pixel of the output. You slide the filter over, second pixel, a third pixel, you slide in the vertical direction as well, and you go on until you've covered the entire input image, and then you get some output like this. I've shown the output deliberately as being smaller than the input, because in general, depending upon what kind of stride you choose for moving the filter, the output need not be the same size as the input. Of course, in the real world, images don't come like this. They aren't these flat 2D structures. You have color planes. So I've shown 3 color planes here, but in general, it can be anything. A generalized notion of a color plane. We call it a feature map. So 3 input color planes, the same color planes in the filter, and they give rise to 3 of these output things. And we sum across the 3 color color planes of the convolved value to get the final output plane. Of course, you don't have to do this with just one filter. You can have a different filter which will give rise to another output plane, and you can keep going on for any number of filters that you want. Mathematically, it's identical. And of course, why would you do this once when you could do it n times? And so you batch the whole thing, and then you work with 128 or 256 or 64 images at once. So this whole thing is, I'm going to call this a multi-convolve problem, and this represents like the main chunk of the work that we need to do on the GPU. cuDNN implements this and a little bit more. Here are a couple of our guiding principles. The first is to have a really flexible API, because people have played around a lot with, for instance, the ordering of the data, the layout. They have different kinds of striding, different kinds of, some people like to crop their images differently. So we like to have an API that supports all of this. So irrespective of what you support in your neural network framework, this should be compatible with that. The second one is to use as little memory as possible, because we know that people like to work with a lot of data and have large models, and we also know that the memory on the GPU can sometimes be limited. So we want to use as little memory as possible and provide as good performance as possible. Of course, that's why you use GPUs, to get good performance. And the final point is sort of an easy integration. We want the library to be easy to work with and interface with. This is the main sort of data structure we use to store our images. It's a 4D tensor. 4 dimensions are N, C, H, and W. N represents the batch, index in the batch, so 1 to 128 or 1 to 256. C is the color plane itself. H and W are, of course, the height and width of the image. We also support striding along each of these dimensions, so you can have your layout. You can you could have the dimensions being N, C, H, and W from slowest varying to fastest varying, or you can have an interleaved format which is N, H, W, C with the successive pixels from each color plane being one after the other. All of that can be handled using these user selectable stride parameters. We also allow you, with this you can play around and access just subsets of your input data without having to explicitly copy them out into a separate buffer. We support implicit cropping, and then we're also planning to handle negative strides, which you can use to implicitly mirror an image without having to go out and duplicate your data and do that explicitly. This is sort of a small snippet of what your code would look like using cuDNN. We start off, we have a set tensor 4D descriptor, which basically is the data structure that you use to store this 4D tensor that represents your image data. There's a filter descriptor, which is another opaque descriptor that describes your data, your filters. And then the convolution descriptor that specifies the parameters of the convolution, for instance, the strides, what kind of padding you want, whether you want to do a convolution or a cross correlation, all of that. The get output tensor 4D is an optional call. It's basically for you to say that, hey, given these input parameters, given this style of convolution, what's my output going to look like? You could query that and we'll return it for you. That will allow you to allocate memory according to what what is required. Or if you already know that, because all of these problems are deterministic, you could just skip that call entirely and do jump directly to the set tensor 4D descriptor. That's where you allocate your output. And then you call the convolution forward that does a convolution in the forward direction. We also support the backward direction implementations of these convolution functions. I've just shown the forward. You can also use the backward convolution or the pooling or the softmax, any of those functions. Before I go into the implementation details, does anybody have any questions so far?
So what is the backward convolution?
It's not really a backward convolution. It's the when you do the training of the convolution network. I'm sorry? The back propagation phase. Yeah, the convolution equivalent of those routines for the back propagation phase. That's what I mean.
So, what's the specific reason behind stride in the batch number, like in the batch index?
The idea is just to keep the notation as general as possible, and we don't want to impose any of these restrictions. Let the user choose whatever format they're most comfortable. Okay, I come from a linear algebra background, so this is very helpful for me to think of things like this. When I think of any linear transformation, you can always represent that as some kind of a matrix operation. And that's sort of the guiding principle behind our implementation. So I'm going to start off just describing a 2D convolution. The 4D tensor convolution that you really do is very similar to this, with just some minor changes. And I'm going to explain this for clarity, and then we're going to jump to that in the next slide. So 2D convolution, you have an image and you have a filter. Start off by putting the filter on top of the image, and then you do a pointwise multiply and sum. You can, if you're looking at this, you can always represent this pointwise multiply and sum as a dot product. And that's how you do it. So you start off with a row vector which represents the tile of your input image. That's I1, I2, I3, I7, I8, I9, I13, 14, 15, the stuff that's in the blue box. And writing it out as a row vector times a column vector, which is the elements of your filter F1 through F9. And then when you slide the box over, you have a new set of 9 image values, input values, I2 to I16, and then another one which is I3 to I17, and you can go on until you cover the entire input image. And what you've done here is basically taken the convolution problem and turned it into a matrix vector multiply. And if any of you have worked with cuBLAS or with any of the BLAS routines, you know that we can do this really well on any hardware through the BLAS library, because it's one of the most commonly used functions. We sort of exploit this. We do the same. We use that idea. But the problem with doing this explicitly is, you see, there's a tremendous amount of data duplication. So if you look at the matrix on the right, I3 appears 3 times in just these 3 rows, whereas in the input image itself, it just appears once. So that's just a tremendous burden, both in terms of the bandwidth that's demanded of the system, as well as the peak memory usage. And this is a big no-no for us. So the way we deal with this is we start off looking at the matrix, the image matrix here. And then if you look at the first tile of it, let's say the first 3 by 3 elements, I1, I2, I3, I2, I3, I4, I3, I4, I5, well, I know exactly where these 5 unique elements reside in the image itself. So instead of going out and constructing this matrix explicitly, I could just construct each tile of it implicitly in shared memory by reading the corresponding elements from the image. And that's what we do. Because what happens in our GEMB implementation, the GEMB is a matrix vector multiplier, is that we read individual tiles of the matrix from global memory into shared memory, and we set up this pipeline of reading it into shared memory and then working on it. So while one tile is being worked on in the FMA unit, you can set up a pipeline whereby you're fetching the next tile from global memory into shared memory. Well, we do exactly that, except the only sort of trick in this is that it's not a straight up fetch of a tile of the matrix. It's a little bit more sort of indexing math that you need to read the specific elements that comprise this tile without ever constructing this matrix explicitly. So we construct the tile I1, I2, I3, I2, I3, I4, I3, I4, I5 directly in shared memory by reading only 5 elements, 5 of the necessary distinct elements from the input matrix itself. This is what the multi-convolve looks like. Instead of having a single filter, you have a bunch of filters. That's the matrix F on the right. And you have these color planes which make our dot products even longer. So instead of having a matrix vector multiply, which is what you had with the 2D convolution, you have a matrix multiply, which is what the multi-convolution is represented as. And again, the philosophy remains the same. When you look at GEM code, or the matrix, GEM is the function for matrix multiply. If you look at any implementation of the GEM code, it has the same thing. You read tiles of matrices A and B from global memory, and while you're reading them, you're working on the previously read tiles out of shared memory. You're doing the FMA work. So what we do here is we basically take our SGEM implementation in CUDA-C, and we modify that to construct these tiles out of the input image directly. So we never have to do all this data duplication out in global memory, and yet we're able to leverage all those FMA sequences from GEM directly. And you can see the additional sort of impact of this. I haven't really talked about this, but if you go back and consider the multi-convolution explanation that I've given you, you have a huge number of input parameters that can all vary. For instance, you have your batch size, which is n. You have h and w, the size of your input. It doesn't have to be square, it can be rectangular. You can have a different number of input color planes, different number of output color planes. Your filter size can vary, your filter strides can vary, your filter color planes can vary. So it's a lot of parameters that you need to take care of. But if you actually work it out and you look at this sort of GEM matrix multiply based implementation, the matrix multiplier's performance depends upon 3 parameters. The number of rows of A's, the number of columns of A, which is the same as the number of rows of B, and the number of columns of B. 3 parameters. And these 3 parameters, there's no magic. It's determined by sort of a product of the subsets of the input parameters of the multi-convolve problem itself. So what happens because of this is that suddenly, instead of having to optimize for 9 different parameters that could go all over the place, you're now optimizing for 3 parameters. You have products of subsets of these inputs, which means that if one of them is really small, then typically the other 2 can be larger and they boost up your overall performance. So you can have a single implementation without having to hyper-optimize for each of these little corner cases that arise due to 9 different input parameters. And this is the performance. I think this is the slide that everybody's been waiting for. The forward convolution function, 3 different implementations. cuDNN is ours, the green line. The blue line is CUDA 2, and orange line is Café. And this is for varying benchmarks, varying batch sizes. I start with a batch size of 128 and go all the way down to a batch size of 4. So it's 128, 64, 32, 16, 8, and 4. And that's how we do. We do fairly well. CUDA 2 beats us on batch size of 128. But the moment you change that down, it drops up quite significantly. The cuDNN maintains its performance. Café is pretty much straight because they process their images effectively one at a time, and so it's not affected at all by a batch size overall. So this sort of illustrates our overall performance. It's about 1.2, 1.3 teraflops on a K40, and it sort of remains stable even as you change the batch size to be smaller or larger as you choose. This is a little bit of news. cuDNN has already been integrated in Café, is out ready for public to use. Same with Torch. Tiano's coming soon. And Jan was quite happy with some of the work that we did as a quote from him. Using Caffe with cuDNN, it's integrated into I think the official 1.0 has a release candidate out. It's just not final yet, but you can download it and use it, play around with it. That's the kind of speed up that you'd see right now using Caffe. The baseline from CPU to GPU and then GPU to our version using cuDNN with all the functions, not just the convolution. I've spoken just about the convolution because that's the main computational workload. But there are a few other functions, pooling, softmax, etc. And when all of that put together, gets a pretty good speed up over Caffe as it is today. This is our roadmap for the future. That's what we have right now. Release 1 is what's out there. We have convolutional layer, the pooling layer, softmax, and some of the more commonly used activation functions. Reasonably high performance on the convolution. Our next release, as I said, this is what we have right now. This is by no means cast in stone. So if any of you guys have any suggestions, any ideas, any requests, we'd be more than happy to hear them. Greater performance, moving on to local receptive fields, which use most of the same stuff mathematically, just different. You can think of it as a reorganization of the same problem. Contrast normalization, fully connected layers, recurrent neural networks. Release 3, something that we'll have to work on is multi-GPU work scaling for these problems. And it's available now. It's free for registered developers. You guys can download it and try it out if you haven't already. It's available for Linux and Windows 64-bit. It supports any GPU that's Kepler or higher. And we also have a version for ARM, for TK1, the mobile platform. If you guys have just tried that out. Well, that's it. That's my presentation. Any questions?
Can you talk a little bit about, you showed the comparison to CUDA Component 2. What's, I guess, what's the trade-off? Why do you do better at smaller batch sizes and they do better at larger batch sizes? I
think CUDA Component 2 takes a different approach from us. They don't use this gem. They do a literal evaluation of the convolution, and it's really, really highly optimized for those sizes. And it does really well. That's why it does so well on the batch size of 128. But that's also why the moment you change, you deviate even a little bit from that, it's quite sensitive to that, to changes in the input parameter space. Anything that it's not super optimized for, it's likely to not do too well.
The Tegra with the 64-bit or the 32-bit on the core that supports?
It's the TK1, Philippe.
32.
Well, the one we said you didn't.
Thank you.
Your example showed a convolution using a 3x3 kernel. Do you support larger kernels?
Oh, yeah. Any kernel size is arbitrary. 3x3 is just,
that's what I figured.
It's any kernel size.
Do you have also any comparison with the H2O library?
The question was about a comparison with the H2O library. We don't right now.
So
we don't have
take that as a roadmap item.
Yeah, okay.
You
I will do that.
So
Definitely. Thanks. We'll try that.
Well, Wendy, this question is too early because I see that on release 3, you have a plan for supporting multiple CPUs.
Multiple GPUs.
Multiple CPUs per node. Do you have any plan for supporting multiple GPUs per multiple nodes?
Well, that's multiple GPUs. We're looking at it. It's there. I know people have played around with it. There's a check-in in Caffe that went out, I think, a few days ago that does multi-node scaling of that. The problem is it's not straightforward. So what we're trying to do here is provide just the low-level mathematical functionality. The way they've done sort of multi-node scaling so far, at least the one that's in Caffe, is effectively, instead of doing a batch of 128, they do a batch of 1024, and they break it up into 8 different nodes, and they work on them independently. The problem is that is not mathematically equivalent to doing 8 of them in series. And so what it means is that if we did that under the hood, it would it will produce a different result for the framework that's using us. And that's not something that we can just do unilaterally. We'll have to work with them to come up with a framework of how to do that. Because that affects things like the quality of your model. And that's not something that's entirely in our hands. We'll have to work to see what the framework developers are okay.
Question. So can you share a little bit about how this library came about and what was the initial motivation for the library?
I think Brian around here?
Yes.
This was a while back when Brian was still at NVIDIA. He was the one who really pushed us to start working on this. You want to talk a little bit about that?
Sure. Well, so I've been working with people in the deep learning community who are using GPUs, and a lot of people were starting to use GPUs for convolutional networks, and there are some great performing implementations out there. I mean, the community is using GPUs effectively, so it's not like people were saying, oh, we don't know how to use GPUs, we need NVIDIA to use them for us, but rather people were saying it's a lot of work for us to optimize our convolutions, and NVIDIA comes out with a new architecture, it seems like every few months. We have to re-optimize, and it just seems like a lot of work, but we've noticed, when we use the matrix multiply routines and BLAS, there's no problem. NVIDIA comes out with a new architecture, and we just link against the library and run it on the new GPU, and performance is great. So we'd love to have a similar experience with deep neural networks. So I thought that was a great idea. I think that deep neural networks are an increasingly important computation, and it's great to see NVIDIA investing in a library that gives users like us performance portability, so that we can write our code once and then have an idea that in the future we're just going to get really great performance on whatever architecture comes along next.
So you also showed a landscape of all the different types of deep learning. Could you go back to that and share a bit more about what your thought process is, and maybe we can get the audience to see what areas people are working in, and potentially give you some feedback about which other areas one could be working with. All right.
That's the one.
Yes.
So broadly supervised and unsupervised, for any of you who don't, who are not very familiar with it, is in supervised you have a bunch of data, and you know what your expected output for each of these input data points is supposed to be. So for instance, if you had a face recognition problem, you know what the name of each person is ahead of time, and then you train based on that, and that's how you perform your training itself. Unsupervised learning, you don't have any fixed labels for what your output should look, what your output should map to. You can think of it almost as giving your machine a ton of data and just spotting statistically significant patterns in it. So some kind of a partition of your data. So for instance, if you think of, let's say Netflix, they have these, a bunch of different parameters that they judge, that they use to sort of tag a movie with. And then they have no idea of, let's say, for instance, we forget about any notion of whether something is a romantic comedy or an action or anything like that. You just take all of this raw data and try and find statistically significant partitions of it. So these movies tend to go together, these movies tend to go together, these movies tend to go together, without worrying about what each of these is called. It could be a genre, maybe not. Same thing with music, for instance. It's just sort of finding some kind of clusterings of the data itself. Shallow versus deep. Deep is where you have a bunch of different layers, where the output of one layer feeds into the next, feeds into the next. Shallow is where you don't have any such thing, where you just give it the input and it pops up. So the convolutional neural net is sort of supervised and deep supervised because, as I pointed out, if you have, you train it on a bunch of data that you know what the output is supposed to be.
So it's structured before the analytics takes place?
You provide it with an expected structure.
And the other one, unsupervised, is just unstructured.
Yeah. I'm sure there are people, as I said, I'm more from a linear algebra background. This is just something that I've been picking up in recent times. I'm sure there are people here who know a lot more about machine learning.
Thank you. Thank you for sharing that. So Sharan is still available to answer any specific questions you may have. And I think there's also many other experts you've talked to earlier in the room. Feel free to join them. If you liked the meetup and the opportunities to network, feel free to give us a 5-star review on Meetup, and we'll strive to continue to produce these kind of meetup for you in the future. And a few notes: if you have any things on your table, make sure you put them in the trash before you go, including the empty bottles and other things. And we have some time before 8:15 here to network, and hope you can join us next time. Thank you.